gentlemen, it is 3:20 in the p.m. It's Friday, but you know what time it is? It's time for some math. So let's get rockin', rock stars. So we've been dealing with this kind of exponential world. On Monday, or I'm sorry, a couple days ago, you figured out how different it is from linears, particularly how fast these things could actually grow. Yesterday, started tearing apart kind of these rules about how if we have all these things being multiplied with powers, how to kind of reduce it so it's easier to look at. And today, well, you're dealing with what happens if I'm dividing all these bases with these big powers, so that's easier to look at. So here's a basic question, right? So like if you have this m to this 91st power divided by m to the 35 power, which would you actually prefer to do, or method to use to actually solve this and reduce it? Well, to answer this question well, you really have to understand what these pieces mean. So we have m to the 91st power, m to the 31st power. Well, m to the 91st power literally means 91 m's being multiplied across the screen. Now, don't worry, I'm not going to write them all out because that's just crazy. But that's going to continue all the way to 91 m's. On the bottom, we have the same. We have 31 m's being multiplied all in a row. Again, I'm not going to write these all out. I just want to give you kind of a sense of what's going on. So 31 m's across the bottom. Now, in essence, as I think Trey in first and second hour, and I don't know who did it in fifth and sixth hour, kind of pointed out, that when you have these top and bottom, they are going to start to cancel one another. Well, you can write them all out and then do the canceling and then count what you got left, but or you can take kind of a shortcut. This canceling effect is essentially substitution. I'm sorry, not substitution, subtraction. So when you see an expression like this, we can actually jump and make this as a simple subtraction problem. 91 m's on the top, 31 m's on the bottom. 31 on the bottom will kill 91 on the top, which will produce a simple subtraction problem, 91 minus 31. Which in the end will just give us m to the 60th power. So if 31 on the bottom kill 31 on the top, we're left with 16, in this case on the top. So which would I rather do? Well, I'd rather take the shortcut personally. If I'm going to write this all out, I could take forever for 91 m's. All right, check this guy out. So now we have this rule. Let's go ahead and reduce it or indicate simply why we cannot. So you guys know some of the tricks we're going to play. The big one that we're definitely going to try to play is this idea of like terms. So please, please, please be careful. Okay, so check this out. We have 11 p's on top. We have 4 p's on bottom. So the 4 on the bottom will kill 4 on the top. 11 minus 4, in other words, will leave us with 7 p's, in this case, on top. Okay? So in the end, we have set p to the 7th power. Let's go down to part B. Well, we have 8 n's on top. We have 5 n's on the bottom. 5 on the bottom, kill 5 on the top. That leaves us with 3 on top, so n to the 3rd. Here, we can't do anything with this, and here's the reason why. We have d's on top, z's on bottom. Nothing's canceling there. So at the end of the day, d to the 6th divided by z to the 3rd is our final answer. Last problem. To do this problem well, you have to kind of acknowledge something on a basic level, and you're dealing with 4 distinct things. You have r to the 7th power as one thing, quote unquote. You have s to the 2nd power, which is another thing. Then you have r to the 4th power and s to the 2nd power. Okay? So in terms of like terms, you can only interact with things that are the same. In other words, the r's with the r's, the s's with the s's. So let's take care of the r's. We have 7 r's on top, 4 r's on bottom. So 4 on bottom, kill 4 on top, leaving us r to the 3rd power, 3 r's. Here we have 2 s's on top, 2 s's on bottom. Guys, that's just gone. Like, that's just going to be a 1. That's the phantom cancel out. So which was just 3 r's. In other words, r to the 3rd power. Moving on. Okay, so we got to consider this big expression, and we have to kind of figure out what's going on. So we have to evaluate the expression for x to the 5th power and y to the 7th power. So if you excuse me, I'm going to grab a calculator because I know that's going to be some big calculation. And we're back. So evaluate the expression for x equals 5 and y equals 7. Well, what that essentially means is I'm going to rewrite this expression, and instead of the x's, I'll use a 5, and instead of the y's, I'll use a 7. So let's get that done. X to the 5th power turns into 5 to the 5th power. Again, I'm just taking this x, 5, or this 5 for this x, and sticking it in for the x. Times y to the 2nd power, but y is 7, so that'll become times 7 to the 2nd power. And then on the bottom, we have x to the 3rd, so that turns into 5 to the 3rd. And then we have y to the 3rd, which will be 7 to the 3rd. So we're just doing a little substitution. Now we actually have to evaluate this, which essentially means work out for an actual like numerical value. Put it in the calculator, see what we get. So let's check this out. So it warns us we could get some big numbers, so let's be on the lookout for that. So let's clear our calculator. 2nd plus 712 is pretty standard now. So on the top we have 5 to the 5th power. Okay, so we have 5 to the 5th power, and we're going to multiply that times 7 to the 2nd power. And then we'll divide that on bottom by 5 to the 3rd power times 7 to the 3rd power. So we hit enter, and it looks like we're going to end up with some kind of crazy answer, 3.5714. So we're going to round that off to 3.5, or 3.17. Let me double check. 3.57. Okay. Alright, so you might be asking yourself, well, what in the world was the point of that? Well, I think we're trying to extract a point here in a moment. So I'm going to rewrite this expression. Excuse me, not this one. We're going to rewrite this expression, x to the 5th times y squared, all over x to the 3rd times y to the 3rd. Okay, and we're going to rewrite this using law of exponents. In other words, we're going to kind of combine the things we know how to combine, and we're going to take care of that in line. So here's the deal. Bam. Let's take care of the red, the x's. So we have 5 x's on top, 3 on bottom. 3 on bottom killed 3 on top, leaving us 2 x's on top. 2 x's on top, or y's on top, 2 y's, or 3 y's on the bottom. 2 from the top, kill 2 from the bottom. That'll leave us a single y in the bottom. So these are actually what we call equivalent expressions, and they're equivalent simply because we're just reducing. It doesn't make this one worth more than this one. It actually makes them worth the same, and let me convince you of that fact. So now let's evaluate this expression using x for 5 and y for 7. So in other words, let's do a little substitution. Instead of x squared, we'll have a 5 squared. And instead of a y, we'll simply just use a 7. Well, I can do actually most of this in my head, I think. So we have this 5 squared, which will be 25. And then we're going to deal with this divided by 7. Okay. So we go to our calculator and we take 25 divided by 7. Oh, look at this. 3. Hey, look, we got, wait a minute. We got 3.57, we got 3.57. The result is actually the same. It's going to be approximately 3.57. So wait, take a look at this. We did the entire expression. We got 3.57. We reduced the expression and then substituted. We got 3.57 also. Well, that tells me something extremely valuable. That tells me that if I want to make my life easier, because let's be honest, I can do that almost in my head, I need to reduce the 2 parts. Or I need to reduce the expression before I substitute, and I'll still end up with the same thing confidently. So did I get the same value? Yeah, I get the same value. All we really did is reduce like some of the redundant parts. Like we didn't need 2 groups of x, we didn't need 2 groups of y. One of each was enough as long as we canceled by rules. This makes this technique actually very valuable. So in the future, kind of keep that in mind. Like we're learning these techniques to make our life easier. Like I know it's hard to learn them, but once you learn them, man, isn't it great? Here's a quick analogy for you. Like at one point, you probably had difficulty riding a bike, but once you learn how to ride the bike, man, did that make your world easier, because you could bike from here to there and everywhere. And if you're like me, I rode my bike pretty much anywhere that I could possibly make it in a whole day before my mom found out I was gone. Alright, so let's take a look right here. So write 4 exponential expressions that are equivalent to this division problem. So let's check this out. If I have a to the 8th, and I divide that by a to the 6th power, along the way to the very end, I'll end up with a to the 2nd power. So what this is really asking me to do is to write 4 more expressions kind of like this, that'll end up with a to the 2nd, which just means that I need to be able to subtract the top and the bottom and end up with 2 for a power. Let me demonstrate what I mean. So I'm just going to pick a number, a to the 100 power. Well, how many a's do I need on bottom so I end up with just 2 overall? Well, the answer to that is going to be a 98. So then that should be the same as, say, a to the 5th. So I have 5 a's. I want 2 a's at the end, so I need to kill off 3 of those a's. I mean, I could do this all day. A to the 9th. Well, 9 a's need 2 a's. That means I got to kill off 7 a's. Let's see what color we have. Purple. Okay. So check this out. We have a to the 20th. So I need to kill off all but 2, so I divide that by a to the 18th. Again, we could do this all day, but here's the point. You have to make sure that the top and bottom powers will subtract and make it 2. Top minus bottom makes 2. You could do that all day. Alright, so you have developed a law of exponents for division and for multiplication. Compare and contrast these laws and specifically mention how you know the base. I will know about the base exponents in each case. So let's talk about these laws. So the 2 laws in question are the multiplication law, okay, the law of exponents for multiplication. I'm going to abbreviate. I'm just going to put it for multiplication. And over here, let's write in blue, we have the law of exponents for division. Okay, so check it. For multiplication, what this basically tells us is that if I have a base to a power and multiply another by the same base to a different power, all I really have to do is add the powers. That's just going to be a to the m plus n. Over here, the division property says if I have a base to a power and divide by something with the same base but a different power, that's a subtraction problem, a to the m minus n. So how are these like, how are these different? Well, they both require kind of similar things. Like, if I were to pick out the biggest similarity, I would say that this requires the same base. In other words, this wouldn't apply if that was like an a to the m and that was like a b to the n. So a as in apple, b as in boy. Like if these bases were different, I couldn't do this. Same as that guy over there. What's the biggest difference? Well, the biggest difference is kind of obvious. One is you're adding the exponents together, which is the exponents of multiplication. And this one over here for division, you're subtracting. Now, as we go through this and we kind of develop some more sophistication, we're going to find that our rules are going to kind of be different and more sophisticated, but for now, I think this is pretty good. Let's take a look at, number 5 on the stain sharp. Alright. Let's get this done. In the following pattern, find the next 3 terms. Well, first of all, you have to figure out what the pattern is. So let's check this out. So 3 goes to 12, get in there, comma, 21, and now we need to figure out blank, blank, and blank. Okay, so 3 to 12, well, how in the world could I multiply a 3, or multiply or add or do something to 3 and get 12? And Miss Fawn's being looked for. Okay, so what can I possibly do? Well, let's try some kind of like some experimentation. Alright, get out of here, other numbers. Turn on a calculator. What in the world? If I go to that. Alright, so let's do some experimentation. What can I do to 3 to get to 12? Well, if I take 3 and add 9, I get to 12. Now, is that going to be the rule every time? Well, let's multiply that, or add that to 9. Oh, looks like I found it. Looks like we're doing some addition here. So 3 plus 9 is 12, plus 3 is 21, so what comes next? So if I add that to 9 again, that's a 30, 39, and 48. And that's what I'm going to be looking for an answer. Let me change this. Okay, so if these are the next 3 numbers in line, let me just get that down here and print. Bam, red. So I kind of got lucky and I just kind of hit what it was the first time, but really there's no secret here. We're just going to kind of experiment. Like, I just tried addition first because it seemed very natural, but that doesn't mean it's going to work every time. Okay, so let's check out this next one. Alright, so we have 3, 12, 48, and we have to find again the next 3 missing terms. Now let me blow this up a little bit. Okay, so let's try the plus 9 thing again. So if I had 3 plus 9, I do get 12, which is a good sign. Here's that 12 right there. What happens if I add 12 again? Do I get 48? Well, some of you guys probably figured out right away, no, it's not. It's going to be 24. It's going to be too small. So the adding by 9 thing didn't quite work. So what's another way I can get there? Well, if I take 3 and I multiply by a 4, that gets me 12 as well. Now here's the question. Is that going to be the same? So if I take that answer, 12, multiply it by the 4, well, look at that. I got 48. Now that's a trustable thing. So what are the next 3 numbers? Whoa, look how big those are getting. Look at that. So I got 48, I got 192, 768, and 3072. Okay, so we found this by multiplication. Now, again, the thing to kind of keep in mind is that it started the same way, 312. But because we changed this by multiplication, this one by addition, well, you can kind of see the difference in how these numbers are growing and how fast they're growing. So over here, when we added 9 each time, the next three numbers only got to 48 total. Over here, when we're multiplying by 4 each time, the numbers got to 3072. So again, world of exponentials, guys. It's all about multiplication. It's about growing fast, and you're going to see pretty soon decaying or going down pretty fast. So I hope this helps. You guys have a great weekend. Get some rest. We'll get ready to tackle this thing again on Monday. Thank you, guys. I'll see you later.